Okay, so welcome everybody to our NGTS seminar class today. Hope you're enjoying the nice weather outside for the past 2 days. Today we are pleased and honored to have Professor Wen-Long Jin with us. Today from Dr. Jin is a professor at University of California, Irvine. He'll present some of his latest research updates on some recent developments in traffic flow modeling and control. Dr. Jin has received his PhD in applied mathematics from UC Davis in 2003. He's a very well-known professor in traffic flow theory community, and he has been on the editorial board of Transportation Research Party and Transportation Science. So with all that said, Dr. Jin, welcome, and the floor is yours.
Thank you. Thank you for coming to this seminar. I heard that my colleague, Professor Mike Allen, came over here last week. I'm glad that we UCI have to kickstart to renormalize the whole thing. Because at the UCI we just hosted our first in-person seminar not long ago. I feel we are relearning a lot of things doing business. I'm glad we are getting back to normal. And I'm really honored and really pleased to come to the esteemed University of Michigan and share with you some of our recent developments in the traffic flow modeling and control. And so, today, I don't know if any of you went to my presentations. My presentation tend to be very technical, mathematical, a lot of formulas, a lot of theorems, and so on. But today, I try to change my style a little bit. Try to focus on, the high-level, discussions on the concepts, on the principles, on the paradigms, and all these things. And maybe some models, but not much so. No on the mathematical analysis proof or numerical empirical analysis part. Okay, that said, if you are interested in any of this, including of course the high level thing, just feel free to stop me, and I will be happy to have discussions with you. And so first I will give a very brief introduction on my understanding what the transportation is and what are the challenges and so on. And then I will get to 3 types of traffic flow models. And actually they turned out to be in different types of spaces, including I call it absolute space on the road. That is when we are driving. We look in the front and the side to have the the absolute distance and so on. So this is definitely clearly very important nowadays for developing driving strategies for autonomous vehicles. So in this space, I'm going to talk a little bit about our ideas on developing provably safe driving models for autonomous vehicles. And then in the second one is the relative space. This is a relatively novel concept, but it actually turns out it originated in a 1991 article, but that was not well known until very recently. Here we consider all the trips in so-called relative space with respect to their remaining distances to their destination. Actually, you've seen that on the GPS devices. It said, ETA, estimated time of arrival, and you can also have, estimated distance arrival in that sense, right? And all these, devices give you ETA, EVA, if we call it, without, referring to the exact origin, destination, routes, links, and so on. So with that, actually, we can talk about different trips in the same unified space, but this is relative space. this turns out to be a really useful view when we look at system level, network level modeling of traffic flow, and then of course management and actually planning. So in particular, I will talk about some bathtub model. Okay, a very interesting name, and later I will talk a little bit about history on that, why it got the name. And then the third one is on the economic space. And this is related to the scheduling cost. So basically, this is more of a hypothesis. At this moment, no empirical data. Basically saying that people shift their departure times from day to day for a reason. Okay, if the reason is to reduce their scheduling costs at arrival time. If there's a kind of no congestion, a certain thing, and then this turns out we will be able to model this day-to-day departure time choice using the traffic flow model. Except that now the travelers they do not drive or run on the roads, but they are driving or traveling on an imaginary road. Okay. So these are three types of spaces. Then associated with these spaces also there are different temporal scale too. So really it should be space-time. Then if time allows, I will talk about two operation and control problems. And one is the high occupancy toll lane. Actually, our first study was highly motivated by Professor Yin's work, and we collaborate on this. But today for this study, we talk about the dynamic pricing scheme for a freeway corridor, where the Professor Yin and Professor Lowe they pioneered in formulating the hotline pricing problem using a point queue model. But we are trying to extend this to multiple interacting bottlenecks, and actually taking advantage of the second type of models, bathtub model. And then also share mobility systems. We will focus on the fleet size management scheme, different types, and to analyze their advantages and disadvantages, again, using the second type of models, so that we can have mathematically tractable formulation for a large network. And then finally, I will offer some discussions on, and also ideas for future directions. In general, I see transportation is entering a very era with a lot of opportunities, not only practically very exciting autonomous vehicle and so on, and also from the theoretical, from those understanding, there seems to be a lot of opportunities too. So whenever we think about transportation, we think about congestion. This, I don't know if this can show here. Yeah, you can see. I mean, this is the Los Angeles area freeway network. Congestion starting way earlier from 7 o'clock actually, and congestion everywhere. However, through the study, we found that in the heart of peak period, morning peak period, actually there is certain level of stationality, meaning that the location of congestion, the level of congestion could be relatively stationary, for example, from 8 to 9, okay? And then also there are other interesting patterns that we can see. Once we commute to UCLA for a conference for 1 week, and we try different departure times, we figure out if we leave Irvine at 6:30, it would take us 1.5 hours. If we left half an hour later, it would take us half an hour more time, meaning that if we leave at 7, we would have to arrive at 9. If 7:30, then it will be 10, things like that. So you can see the congestion is building up. But the pattern was pretty stationary, pretty clear. And actually, even we fix at 6:30, so we arrive at 8 because the workshop start at 9. So we want to arrive a little bit earlier. And actually, we would have met one motorcyclist every day. They have the Captain American shield on the back of the so we can recognize them. So it just suggests that there's a kind of there's a stationary traffic pattern, and also pretty reasonably stationary pattern in departure time, in our choices, in all of this, right? So then, of course, now is an exciting time. This is UC Davis definition of 3 revolutions. Many people would argue that we've seen this for a long, long time already, right? This is not, this is just kind of surfacing again, but electrification, automation, shared mobility, all of this make transportation even more exciting field to get into. Okay, and also that is good news. Bad news might be many researchers, people from other fields, they are all coming to transportation. Okay, computer scientists, all those people trying to study transportation. Then transportation may not be as simple as many of those colleagues think, right? Because transportation has a lot of stakeholders, cars, travelers, and roads, and so on. Actually, because of the transportation system involves human beings, and there are a lot of behaviors, a lot of at different levels, from the lower level engineering, choices like car driving on the road, and then to a little bit kind of like an economic choice on the route choice that's associated with costs, maybe lane choice too, but of course there's no clear cut differentiation between this, and then the choice of arrival time, departure time, and then the trip choice, destination, and so on, and then all the way to the social. Because many of times where we are living, whether we are working, and all of this is not really determined by the transportation alone, at least. Okay, so now with the autonomous vehicles, we can only have even more players. Even Google, even Apple, Tesla, definitely they are getting to directly play in the field of transportation. And there's a clear hierarchy of all kinds of behaviors. But at the same time, I like to view a transportation system as on the this right figure as a control system. So we have a transportation system with all stakeholders, interactions among the different components, and they have a different performance on safety, comfort, mobility, equity, livability, accessibility. You can think about all kinds of performance measures. But then, of course, many of the time these are not as desired as it can be. We have some desired performances, and then we would compare them and to see the gaps and try to use some control management, planning, design strategies. Try to alleviate, try to mitigate, try to fill the gaps and so on to make the transportation system more efficient, safer, and make the life better in general, right? So you can see that transportation system is really complex. With especially, it's not only just an engineering system, with the social system, and we should really try to take advantage of different kind of research methods. Traditionally, there have been first principle methods, like a Newtonian paradigm, basically to discover the fundamental principles from the first principles. Okay, and then to analyze them, to derive the conclusions, and so on. Second type is data-driven. Observation experiments generate a lot of data, and then using statistic methods and so on, try to infer some knowledge. Now very hot, very popular method is using machine learning to learn about people's behavior, for example, driving behavior analysis. Third type is relatively recent with numerical simulation, and with more and more powerful computers, and this become more and more important for studying, understanding such complex systems as transportation systems. And ideally, all these methods should work together. Right? And there are disadvantages and advantages of different type of methods. While many of my research actually started from first principle, I always try to identify some simple, intuitive principles and then try to see how far we can go, whether these principles will lead to some interesting, useful models, concepts, and so on that can help us to understand the complex transportation problems. And first principles, they are very important, basically in the research and also actually in engineering. Well known now is Elon Musk use the first principle to design the new engineering system solutions and so on. So principles actually have been used everywhere because it's axioms, assumptions, postulates, hypotheses, except that many of the times these have been taken for granted, implicit in a sense. But since assumptions, we know that the assumptions actually many of times would determine the quality of the results. And we need to take a closer look at the assumptions. Why the assumptions are reasonable. Whether we can still use the same assumptions in the new era of autonomous, connected vehicles. And this exercise turns out to be, very critical when we get to design, driving models for autonomous vehicles. Because, driving models, there have been a lot of car following lane changing models in the literature. But they were designed in the area for understanding traffic flow. And any of you been playing with a traffic simulator like recent, especially when it involves lane changing, vehicles can overlap with each other. That's okay, right? Who cares about it? But if we are going to use this driving model, this lane changing model to control autonomous vehicle, then that would be problematic. So it just suggests that maybe when we design, when we develop those models, we might omit the very basic safety principle in there. Okay, that is okay for management, for those kind of scale problems. But if we want to get to control, to say it's a kind of describe behavior, that's okay. There's some errors. There's error everywhere. But if we want to use those to prescribe the trajectories, control the trajectory, then there will be problem. But then, does that mean we want to discard all of this model altogether? Actually, that has been pretty popular proposal. Saying that, okay, we have AI. Who needs this car following model, this simplest model at all, right? But I would argue that there are still some useful principles, useful knowledge that we can take advantage of from those. So hopefully, ideally, as I said earlier, to solve such complex problem, ideally we want to take advantage of whatever resources, whatever knowledge we have accumulated so far. Okay, try to push them towards their limit or even beyond. that could save us a lot of things, maybe including lives. Okay. But that is because, autonomous vehicles, some people have already claimed that we've already entered the winter of AVs. I don't know if you heard about it. Because there are a lot of challenges, like the very high-profile accident by Uber's autonomous vehicle. They just drive through the pedestrian, and then there are Tesla. There's a lot of accidents, and Google Waymo driverless car. They've been doing a pretty good job. They were only rare collided by other vehicles, but never caused any accident by themselves, as far as I know. But they've been stopped by policemen for a couple of times because they are going too slow. Okay, we know that there's a trade-off between going fast, be efficient, and safe. So obviously, this is not good either. We want to be safe and efficient at the same time, ideally, right? So, what would be the ideal driving behavior of AVs? Definitely, there will be safety. There will be studying showing that some of you might be doing research in this. Human-driven vehicles probability fatality per hour is 10 to -6. Some people use mileage in similar order. And some would argue that for general public to accept AVs, it's better to reduce the probability of fatality by 3 orders of magnitude. Some other people say we can relax this, but still, that is really, really challenging because what does this mean? This means that we should really cover 99.99%, lost track of the 9% of the cases. But whoever you've been working in traffic engineering, and you know that, we will be satisfied if we can cover 85% time, right? But that is a huge gap. And then we also want to be efficient, right? We do not want this to be too slow. And even more challenging is to have some human-like, behavior. Because in the initial stage, we got to have a mixed autonomous vehicle and a human-driven vehicle. And then we want to have a similar behavior, but then how do we define such kind of behavior? For example, human-driven, human beings are really intelligent. We can communicate with each other. Take, for example, lane changing. If you signal your lane changing, to the left or to the right, and the following vehicle just slow down a little bit, then you know that, this driver is really nice. You would wave to them maybe, and then you just switch in, right? So there's certain trust and communication there. Can we reach that level of intelligence for AVs? Or even how do we define this kind of trust, this kind of thing at all, right? So a lot of challenges. And it's not as easy as computer scientists or deep learning people. Oh, we solved the problem, okay? Like Tesla, right? They claimed, or whoever, I believe Elon Musk claimed they would have fully autonomous vehicle. Some time ago, I lost track. They can change the things too. But the general principle still, we can use some general principle to design AVs as intelligent robots, to divide the driving task to sensing, to planning, to action. This intelligent robots. But actually, I would argue, when we get to autonomous vehicles, probably we should have more hierarchies, more layers of tasks. For example, sensing, sensing is good. But we also need to have some perception, understanding of what it means, sensing. For example, the followers slow down a little bit, then our perception is that they will let you cut in. Okay. Then the planning too. Planning should also depend on certain prediction of the future status of the leader, of the pedestrian, and all of this, right? And the action, basically just how to accelerate and so on. This one is considered to be well understood, because this is pretty much, when we get to this level, it's pretty much like engineering problem, or electric or mechanical engineering problem. Those are much easier to solve, while the sensing, perception, prediction, planning, they are much harder. Okay. So among these tasks, the sensing, perception, they are really, really challenging. But the good thing is that they can be tested in the relatively closed environment, like really, really nice MCT. These test tracks, okay, to detect, to test all these sensors and so on. While the planning part, actually, we really have to do it in the real world, okay. Even though it's not so complex in terms of the factors, the variables probably. However, we have to do it in real time, okay. And then basically that means if on the planning side, we can take AI approach, statistic approach, or we can take a mathematical approach. If we are going to take a statistic approach, okay, there's a statistic guarantee. Then that means we really, if we update one line of code for such planning, trajectory planning, we better to retest the whole thing for another billion miles. That is at least very costly. Okay, even Waymo, even Tesla, you test for a lot, but they've been changing all the time too. But this is where the mathematical, the first principle approach could be helpful on the planning side. Given the defined sensing and perception, and if we can design something that is mathematically guaranteed to be safe, okay, that is not just 10 to -9, that is 10 to -infinity, okay, and that saves a lot of efforts and so on, so on. So then again, but we are just talking about planning, right? While for sensing perception, right now, mathematics, first principle could be useful, but we have to develop others. While this planning, as said, is we can still take advantage of car faulting models, and there will be the adaptive cruise control and this AI. There are different approaches, but the car faulting models still have the advantage that they are mathematically tractable. Okay, so maybe we can take advantage, but it's not easy task. As I said earlier, many existing car faulting models, they just violate the safety principle directly. Then that means 100% guaranteed crashing. Okay, so if they violate it, then that is also 100% guaranteed. So that has been the motivation. Actually, first we were motivated by some testing on the robotic cars. As said, I come from traffic flow theory background. I'm used to see the vehicles cross each other and so on. No big deal. Nobody cares about it, right? Just a number. But when we implement this on this robotic, robotic cars, I was still shocked to see them crash into each other. Okay, so that is where I got motivated on this. But I'm not going to show this. I guess I need to speed up. But then, what kind of first principles, right? Some people, developed a very famous cross model. In his dissertation, he said that there are no first principles. Traffic flow is just too complicated. No first principles. And but Genzo did not agree with him. And there should be some laws. Okay. And actually, it turns out back in 1945, a couple of physicists already were trying to derive traffic flow model from safety principle already. Actually, they already derived fundamental diagram, already derived a car falling model. But this is not so well known, even though it was cited by Newell in 1961, but it was lost in the literature. I'm not going to get into the details of this, but there are some first principles. But before that, we need to define it to provide a view of traffic flow in the absolute space. Okay, we have bunch trajectory, and these bunch trajectories can be viewed in the 3D surface of time, of space, of cars. Okay, but you see that these cars can be considered as people, right, or social. So we do have space, time, and social dimension. And then we can define different variables, different coordinate system, and then actually we can define some first principles related to planning or trajectory planning here, basically. For example, collision-free. Okay, with respect to spacing, should be bounded spacing. Bounded speed, for example, should be forward traveling and not much higher than speed limit. Okay, and also if we want to improve the efficiency, generally we want to maximize our speed under all constraints. And then there's a fundamental diagram. It says fundamental diagram actually derives from the safety principle. And the bounded acceleration, bounded jerk, and so on. And this first principles, fundamental diagram, for example, actually is supported by data. Okay, such a kind of triangular fundamental diagram, which captures the speed limit, captures the jam density, jam spacing, and it captures the interaction when vehicles getting closer to each other. They tend to drive slower. That makes sense, right? However, it said in some models, including very famous General Motors model, right? The General Motors car falling model probably is the first car falling model that we learned. It just directly violates the principle, meaning that the vehicles can drive at really high speed when they are bumper to bumper. That is not right. If we want to use them to control autonomous vehicles, or I would argue to describe reasonable driving behavior, that should also be problematic. But then, again, there are so many other sources for errors. Sometimes it did not matter, maybe. But then we can use all of this, try to show some interesting relationship in such principle. This principle is just once you define them, it just makes sense, right? Those are basic requirements. Like a collision-free, their distance cannot be, spacing cannot be smaller than jam spacing. This called collision-free condition actually turns out to be highly related to CFL condition. I don't know if any of you familiar with fluid dynamics. That is to guarantee the numerical stability, convergence, consistency of numerical solution methods. Turns out they are equivalent when we have so-called concave fundamental diagram, and if the fundamental diagram is non-concave, turns out the collision-free condition is more restrictive than the CFL. Or meaning that if you just satisfy CFL, that is a mathematically motivated condition. Mathematically still well defined, but cars will collide into each other. So that means probably just using existing mathematic concepts is not sufficient. Okay, we want to improve things. Actually, by introducing collision-free condition, can help to resolve such issue. And another thing is that we've done some study. If we introduce a bounded acceleration to the model, it turns out this can describe the very well-known capacity drop phenomenon. Not only qualitatively and also quantitatively, can be calibrated and verified with this result. Can match the trajectories of vehicles very well. Okay. So there are 4 vehicles that were sent through this Kobutoki tunnel in Japan in 1980s, and they plot the speed profile at different locations, and we can clearly see that this is the active bottleneck, meaning that after this, vehicles will accelerate and then there will be free flow. But inside this already, there's acceleration and the acceleration profile, and actually can be predicted by a simple LWR model, which basically is just a conservation law plus a fundamental diagram, plus a boundary acceleration constraint, and so on. So, and then with my PhD student, Irvine Martinez, and basically done by her, she actually extend this model to decide the optimal location of variable speed limits. Okay, so the idea is that if the variable speed limits location, the sign here, if it's too far away upstream, then the queue can block the upstream off ramp and so on, and disrupt other traffic flow. But if it's too close, then it cannot help to improve the throughput by eliminating the capacity drop phenomenon. And she actually managed to find to formulate and solve the problem, an optimization problem based on the understanding of the traffic dynamics inside the bottleneck and outside. And then another recent task actually is to try to develop the reasonable driving model by introducing boundary deceleration. We know that if it's infinite deceleration, okay, this is trajectory of the vehicles. Infinite deceleration, then there's not much safety concern. Okay, but just limited deceleration, then how we can model this, and also to make it mathematically guaranteed. Okay. And this is also related to one well-known debate or criticism and the resurrection of second-order model. Dagenzi in 1995, criticized existing second-order model, continuum model, but now we know that continuum model, car-falling model, they are all equivalent, just in different coordinates, different formulation. Just showing that some would lead to backward traveling. Okay, this actually is using one of the principles, while the other one, the criticism more well-known, is so-called non-anisotropy. He showed that for some model, the homogeneous system, characteristic wave speed is larger than vehicle speed. Then he argued that the information travels faster than vehicle. Then that's not reasonable. And then there have been the resurrection efforts, okay, including well-known All-Rescue-Zhang model by designing model with characteristic wave speed less than vehicle speed. But actually, now, I think this model, All-Rescue-Zhang, including General Motors model I mentioned earlier, they all violate the collision-free condition. So they are not safe. So they address the criticism, but propose some very unsafe model. So something got to be wrong. So I would consider the criticism is misplaced in the sense that they did not take care of the very fundamental principles. Okay, while looking at this is a kind of secondary, even purely mathematical discussions. So all of this can be criticized using these first principles. So I guess I use quite a bit of time already. 45 minutes. So did I use 45 minutes or including the introduction, or how much time? Maybe I should listen.
Yeah, 10 more minutes. You can.
10 more minutes.
Yeah.
Okay. I just finished the first topic, but again, I don't have to finish everything.
Yeah, you can have more.
Yeah, then very interesting. I definitely want to talk about the relative space, right? Earlier I gave the introduction. In the traditional transportation system analysis, we always divide the network into traffic analysis zones, origin, destination, routes, nodes, and links, right? Like, and then describe them, the trips according to the OD pair, routes, and so on and so on, right? But if we introduce this relative space, which is a remaining trip distance, all of these trips can be put in the same time-space diagram. Okay, basically all trips would start with some trip distance and then keep decreasing, and when it is zero, then it reaches its destination, and we can put a lot of trips here. And here, we don't care, where exactly they work. So this interesting, very interesting view, and then we can put all the trips, for example, in the network, as large as you like. Show the trips in such the top, figure like this. 24 hours, and X is the remaining miles, remaining trip distance, and then each curve or line, this is the multiplication, we consider a trip. They have different starting distance, starting time, but they are all decreasing, and when they get zero, they reach their destination. So all this X is relative with respect to their own destination, their own route choice, and so on. And all of these are hidden. Okay, of course, in reality, is there, but they are hidden. And if we consider the whole system, we know that in the whole network, with multiple interacting bottlenecks, the more vehicles in the network, the more congested it is. Just like this group, more, and then they will cause some congestion, stop, and so on. So that can still be a very useful simplification, can still help to capture some dynamics. And then actually we have the model. I don't have time to get here, but assumption here is that we are using relative space X, and we use so-called network fundamental diagram. Assume the average traffic speed depends on the number of vehicles in the network. That makes sense. The more vehicle, the lower speed, right? And then conservation, and then we would reach such kind of PD. And if we assume the trip distance follow a time-independent negative exponential distribution, actually this can be simplified to an ODE. This actually turns out to be the very famous, very hot, topic in the recent traffic flow community. It's Mfd Based Model. I don't know if you've heard about it. Initiated by D'Agenzio, 2008. But it turns out Small and Chu has this already. But it turns out Vickery had this in 1991 in an unpublished manuscript. And when I was studying the problem, then I got a copy from Columbia University and got it. And it turns out the first page he talked about it. And he clearly stated all the assumptions that you need to derive the ODE. Turns out, Small and Chu and D'Agenzio, they all did not explicitly state the condition on the negative exponential distribution, such that many followers actually use this model incorrectly for constant trip distance and so on. So that is something very interesting. So I always say the transportation field is pretty young, 1940s, 1950s started, right? It sounds like a lot of time, but put in the history of science, this is a really young field, and we should go back and read the literature all the way back. There are a lot of great ideas, and Vickery exactly derive things from the first principles, from the assumptions, and clearly state them, and then derive the very nice model. But they were rediscovered, reinvented Now this citation before the publication of the 2020 version that I and Professor Richard Arnold helped to edit this and publish in the Economics of Transportation. This was not well known at all, just a handful of citations. But if you check out the citation of D'Agenzo, even small and true, hundreds, thousands of citations. Okay, but I have to say that Vickery did it earlier and did it better in this case. And then other work too. But comparing LWR model and generalized bathtub model, we see that there's a lot of similarity. Except that one is absolute space, the other relative space, and there are parallel development, and there are a lot of possibility.
Can I ask a quick question?
Mm-hmm. Yeah.
So in what sense is the relative? Is you talk about the x is the distance remaining?
Yeah.
In that sense, okay.
Yeah, exactly. There are remaining distances. Yeah. So, and actually, in our recent study, we found that it's more than just a model. Actually, this represents a new paradigm for transportation system analysis, actually. Not just for traffic flow modeling, and also for planning, for everything, okay? So, I don't have time to get to this, but basically, this is another view. And one really nice property, actually, is related to, the absolute space. If you are tracking people, origin, destination, route, and path, and so on, their personal identifier information. Their house, their office, and this. But in this relative space, no, you don't know anything, right? You just know how far they are from their destination without knowing where their destination is exactly. So this actually is privacy preserving. And this can have really profound implications in many regards. And we are extending this and not only to solve the traditional problems and actually try to address the privacy issue and also equity in the data collection.
But you still have to know the destination, right?
No, we just need to know how far you are from your destination. You don't have to tell me where your destination is. You just, every time you tell me, at a certain time, how far you're away from, just like estimated distance to arrival.
Right, but I understand if you talk about one aggregate model, then that should be the assumption you make, right? But if you look at a network,
yeah, same thing.
For example, link distribution, you have to know the flow at each link.
No.
Do you need to know the destination?
No. Yeah, you just tell me your distance to your destination at different time. Then you give me a bunch of points, right? I link them, and this becomes the trajectory that we can get from shown here. All these trips have totally different destinations, routes, links, and everything.
But that can give you the average narrow speed.
No, we can calculate from the network average speed.
Right?
Yeah.
But how about I'm asking about each link.
Well, each link, that depends on your interest. If you are interested in each link, of course,
right,
you will get that. But if you are just interested in the network level, then you don't need it.
Yeah.
Depends on your, study.
Okay, can you go to the slide?
Mm-hmm.
You talk about traffic assignment, right? When you compare that, it's that there's a traffic assignment and the TAZ. The purpose of there is to get the link distribution, right? Distribution, try to estimate the flow on each link or traffic speed in each link.
Yeah. So this is of course traditional way of viewing traffic assignment.
Correct.
Now maybe we don't have to look at that detail. So anyways, that's very computationally expensive, thousands, a lot of things. Maybe we just look at by zones.
Right, even by zone, you have to know if you consider spatial heterogeneity.
Yeah.
Then you have to consider destination.
Oh yeah. There will be destination, but the destination can be much closer. Right. Okay. Yeah. Then you can talk about even actually we are doing some work. You can consider the whole freeway network as one network, and we don't care which on ramp you get on, which off ramp you get on. You kind of get what I mean. So it depends on of course. I mean, if you are interested in a link level, probably this model is not that useful anyways. Probably you want to get back to the traditional. I mean, but for large scale network, this kind of thing, this provides a really nice simplification. Just like a bathtub model. Bathtub model is not a replacement of LW model. LW model is a nice in addition or complementary. And third one, well, I briefly talked about it, and the basic message is that we can talk about this departure time choice as a traffic flow problem, just on an imaginary road. And I was totally motivated by all the debates with Professor Hai-Yang and others, and they show that this day-to-day choice on departure time is not stable, and then they want to conclude after examining 5 or so many dynamic systems, and they try to conclude that no, I mean there's no stable departure time choice pattern. I said no. According to my experience, I said earlier, the commuting to UCLA, there is pretty stable scheduling pattern in my experience, and also I said logically, you show 5, even if you show 5 million, they are not stable. Does not mean there's one hiding somewhere that's still stable. You get me? And I'm totally motivated by that. Actually, earlier I already knew the instability back in 2005 or so. But I always believed there should be stable one, so I did not publish, did not do that. But anyways, then I went ahead and tried to construct one based on some simple principles, and then convert that to a traffic flow problem, and then show that it could be stable. But interesting thing in this context is that it said the travelers effectively traveling in the economic space, and I don't have time to talk about this thing, but I said these are all based on the bathtub. This view can be very useful to provide mathematically tractable formulation for network problem with many interacting bottlenecks, on ramps, off ramps, and so on and so on. So basically the idea is to use bathtub model, and then we have a simple distance-based dynamic pricing scheme. And actually, we can mathematically prove that closed loop system is stable and has an optimal equilibrium point. This is not sufficient, but this helps to design the practically viable scheme in the real world. And then for shared mobility system, we basically show that definitely the pooling rate and the extra mileage rate, and very important, and also the current practice by Uber, by them, that try to minimize the waiting time is not viable. Actually, can increase congestion. I mean, if we really want to reduce congestion, we have to cap the number of vehicles in the network. And we provide some, again, bathtub models, some mathematical discussion and formulation on this. So I want to get to the discussion part. So now you get to next generation transportation system, right? Definitely a lot of new opportunities, challenges. But I do believe this first principle, concepts, models, and all of this, and space-time, they are all relevant, and maybe even more relevant than before. And the first principle approach, it can still be a very important approach to solve a problem, to provide mathematically guaranteed properties. This will help us to save the expense on the tests, for example. And then, the theory just alone can be very useful because this provides some common language to clarify concepts, inconsistency, contradiction, in the literature. So in general, we need all. I'm not saying that everybody should only use one, and everybody should work on this. If you are interested in artificial intelligence and all those, good. I think, but still maybe can still benefit from first principle. This kind of approach, this kind of language, this kind of thing. And then depending on your style, for example, my style, I like to work in small group, and read literature, not organize, all tests. I have a heavy weight on the first principle approach. But at the same time, I'm paying attention to the data. We've been doing a lot of data analysis, and even robots. We developed some simple robotic car testbed. And yeah, getting to that, space-time, that's very interesting. We know space-time is a really fundamental concept in the physics. Like Einstein's general relativity, it's just a new interpretation of space-time or equivalence. But our transportation system or social system in general, we have space-time people. If you are from China, you might know that, the 天地人. Okay, it is. So this is much more complicated, but there got to be some thing we can learn from each other. And for example, we can maybe if we can define the right space dimension, we might be able to formulate the dynamics in society, social spaces. But then again, what should be the proper space? We don't know, but then we can use this to study social mobility, equity. People talk about social ladder and things like implicitly there got to be some space there, and so on. So, yeah, in general, my view is that definitely the transportation is an important component of society. I'm biased, but I would even further want to say that maybe transportation is society. Okay, so all the challenges, all the opportunities are there. So, yeah, thank you very much. Any questions, comments, or any stories to share?
So building on Dr. Yin's question on the bathtub model that you had, distance, space, distance to destination model. So do you assume that every traveler is sharing their destination and distance with you? Like, do you have
share the same destination?
No. Are they sharing the information with you? Do you have the full information of everyone's?
No. Yeah. For example, when we collect the information, ask everybody to report. You just need to report the timestamp and how far away you are from your destination.
So, but everyone
as long as you are in the network that we are concerned with, of course. Yeah, we don't care where you are really going, which route you are going.
Because in linked level models, you don't need, like, you can have like loop detector data, whatever, to measure the performance on each individual link. But here you need the entire information from everyone, right?
That's a good point. I mean, definitely, we there's a potential to, have privacy preserving. Actually, I've been working on one with one master student to show it's possible. But what kind of detector we want to have, and things like that, there could be some. But at least GPS, for example, GPS can do that already. Just report it. But you save your own route. You still use those for navigation. But when you report, just report this kind of relative space information.
So, yeah. So it's assuming that you do route choice as well, like
no,
or they know their route, right?
Yeah, they know their routes.
So, do you go into details of choosing that route or?
No, I mean definitely there's a route choice problem can be defined. If we have multiple bathtubs, for example, then you have one zone and couple of other zones. Each one is a bathtub. This is actually related to multiple bathtub model, traffic flow model too. You can do that, but then definitely there's lots of information. This is a cost that we have to pay a price, but it seems to be sufficient for many studies, for maybe network level management, for cordon-based pricing, for all those level problems. It won't be useful for solving local. Whenever local information is relevant, it's important. Then this probably is not a good approach. But for large scale, for multimodal choice and things, this can be pretty useful. Maybe starting point. Then you still need to get more detailed. Just like in absolute space, the same thing. We may start with cell transmission model, but then we still want to use some car volume model and get more details. Yeah, this is complementary. It's not meant to replace all things.
On the topic of the day-to-day equilibrium model, one of the impressions I got from looking at the problem and from reading was that it's really hard to achieve stability without some sort of history or maybe like look ahead in a sense. I was wondering if that's what you used in your work, or if you managed to sort of avoid that.
Yes. This is a really good question. We do have some discussion with other colleagues regarding day-to-day departure time choice. You got to have some knowledge regarding the current day or the past days, right? So here, actually, as a first attempt, I was pretty, how to say, very generous or very relaxed in this assumption. Assume we know all information, the current day, how many people arrive at a certain time, and what is their queuing time, scheduling costs. Assume everything's known. However, actually, it turns out one biggest distinction between this model and the existing model is that existing model assume that people can switch to any departure time that has lower cost at a kind of global scale. But this turns out to be local in the sense that they just search the arrival time around them. So, in fact, I do believe this one actually requires much less information in that sense. You just need to know people who, that's still in high order, you just need to know people who leave a little bit earlier, a little bit later, and their costs, and then you evaluate. So there's a